Hello students, in this video we are going to discuss about the concept of pipelining. The speed of execution of programs is influenced by many factors. One way to improve the performance is to use faster circuitry technology to build the processor and the main memory. Another possibility is to arrange the hardware so that more than one operation can be performed at the same time. In this way, the number of operations performed per second is increased even though the elapsed time needed to perform any one operation is not changed. We have encountered concurrent activities several times before. The concept of multiprogramming and how it is possible for I/O transfer and computational activities to proceed simultaneously is being discussed in the unit 1, and the direct memory access device makes this possible because they can perform I/O transfer independently once these transfers are initiated by the processor. Pipelining is a particularly effective way of organizing concurrent activities in a computer system. The basic idea is very simple. Let us take an analogy. Here in this analogy, Anne, Brian, Kath and Dave each have one load of clothes to wash, dry and fold. Let us assume that washer takes 30 minutes, dryer takes 40 minutes and holder takes 20 minutes. Here, since there are 4 loads, what they did is for 30 minutes the clothes is being washed, and after that the cloth is being dried for 40 minutes. Then the user took 20 minutes for folding the clothes. After that the second load is being taken and the washing, drying and folding process is being completed. Similarly, the same process is being executed for other 2 loads of clothes. So the total time taken by the total time taken to complete the process is coming around till midnight. Instead of completing a load and after taking a load in traditional pipeline, what they are doing is that while the first load of cloth is being washed and it is being dried, the second load of cloth is being washed. When the first load of cloth is being folded, at that time the dryer is being ideal, so the second load of cloth is being dried. While the second load of cloth is being dried, the washer is being completely free, so the third load of cloth is being washed. When the second load of clothes is being folded, the dryer is free, so the third load of clothes is being dried. So the total time taken for completing all the 4 loads of the clothes to wash, dry and hold comes around 3.5 hours for 4 loads. But if it is being taken as an individual task, the washer took the task to complete till midnight. But now it has been ended fast, and the total time taken for the laundry is of 3.5 hours only. Consider how the idea of pipelining can be used in a computer. The processor executes a program by fetching and executing the instruction, one after the other. Let Fi and Ei refers to the fetch and execute step for the instruction Ii. The execution of program consists of sequence of fetch and execution steps as shown in the figure. Now consider a computer that has 2 separate hardware units, one for fetching instruction and another for executing them as shown in this figure. The instruction fetched by the fetch unit is deposited in an intermediate storage buffer B1. This buffer is needed to enable the execution unit to execute the instruction while the fetch unit is fetching the next instruction. The result of execution are deposited in the destination location specified by the instruction. For the purpose of this, we assume that both the source and destination of data operand on by the instruction are inside the block labeled execution unit. The computer is controlled by a clock whose period is such that the fetch and execution step of any instruction can be completed in one clock cycle. The operation of computer proceeds as shown in the figure. In the first clock cycle, the fetch unit fetches an instruction I1, that is of step 1, and store it in the buffer B1. At the end of the clock cycle, in the second clock cycle, the instruction fetch unit proceeds with the fetch operation for the instruction I2, that is step 2. Meanwhile, the execution unit performs the operation specified by the instruction I1, which is available to it in the buffer 1. By the end of the second clock cycle, the execution of I1 is completed and the instruction I2 is available. Instruction I2 is stored in B1, replacing I1, which is no longer needed. So step 2 is performed by the execution unit during the third clock cycle, while the instruction I3 is being fetched by the fetching unit. In this manner, both the fetch and execution unit are kept busy all the time. If the pattern in the figure can be sustained for a long time, the completion rate of instruction execution will be twice that achievable by the sequential operation depicted in this figure. So in summary, the fetch and execution unit in this figure consists of two-stage pipeline in which each stage performs one step in processing an instruction. And internal stage storage buffer B1 is needed to hold the information being passed from one stage to the next. New information is loaded in this buffer at the end of each clock cycle. The process of an instruction need to be divided into only two steps. For example, a pipelined processor may process each instruction in four steps as follows. Fetch, that is read the instruction from the memory. Next is of decode, that is decode the instruction and fetch the source operand. Next it is of execute, that is perform the operation specified by the instruction. Finally, it is of write, store the result in the destination location. I will repeat it. First is of fetch, next is of decode, then it is of execute, and it is of write. So fetch is to read the instruction from memory, decode is decode the instruction and fetch the source operand, then execute is to perform the operation specified by the instruction, and write is to store the result in the destination location. Right. The sequence of events for this case is shown in the figure. Four instructions are in progress at any given time. This means that four distinct hardware units are needed as shown in the figure. These units must be capable of performing their task simultaneously and without interfering with one another. Information is passed from one unit to the next through a storage buffer. As an instruction progresses through the pipeline, all the information needed by the stage downstream must be passed along. For example, during the clock cycle 4, the information in the buffer is as follows. That is, buffer 1 holds instruction I3. Buffer 1 holds instruction I3. during the clock cycle 3. Sorry, clock cycle 4. During clock cycle 4, buffer 1 holds instruction I3 which is being fetched in clock cycle 3 and is being decoded by the instruction decoder unit. Buffer 2 holds both the source operand for instruction I2 and the specification of the operand to be performed. This is the information produced by the decoding hardware in cycle 3. The buffer also holds the information needed for the right step of instruction I2, even though it is not needed by stage of execution. This information must be passed on to the stage right, that is W, in the following clock cycle to enable the stages to perform the required write operation. The buffer B3 holds the results produced by the execution unit and destination information for instruction I1. Now let us discuss the role of cache memory. Each stage in a pipeline is expected to complete its operation in one clock cycle. Hence, the clock period should be sufficiently long to complete the task being performed in any stage. If different units require different amount of time, the clock period must allow the longest task to be completed. A unit that completes its task earlier is ideal for the remainder of the clock period. Hence, pipelining is most effective in improving the performance of the task being performed in different stages require about the same amount of time. This consideration is particularly important for the instruction fetch step, which is assigned one clock period in the figure which I have shown previously. The clock cycle has to be equal to or greater than the time needed to complete a fetch operation. However, the access time of the main memory may be as much as 10 times greater than the time needed to perform basic pipeline stage operation inside the processor, such as adding two numbers. Thus, if each instruction fetch requires access to the main memory, pipelining would be of little value. The use of cache memory solves the memory access problem. In particular, when a cache is included on the same chip as the processor, access time to the cache is usually the same as the time needed to perform other basic operation inside the processor. This makes it possible to divide instruction fetching and processing into steps that are more or less equal in duration. Each of these steps is performed by a different pipeline stage and the clock period is chosen to correspond to the longest one. Now let us discuss about the pipeline performance. The pipeline process is being shown previously and it completes the process of one instruction in each clock cycle, which means that the rate of instruction process is 4 times that of sequential operation. The potential increase in performance resulting from pipelining is proportional to the number of pipeline stages. However, this increases would be achieved only if pipelined operation as depicted in the figure would be sustained without interruption throughout the program execution. Unfortunately, this is not the case. For a variety of reasons, one of the pipeline stage may not be able to complete its processing task for a given instruction in the time allotted. For example, stage E in the fourth stage pipeline of the figure is responsible for arithmetic and logic operation, you assume it, and one clock cycle is assigned for this task. Although this may be although this may be sufficient for most operations, some operations such as divide may require more time to complete. So The figure shows an example in which the operation specified in instruction I2 requires 3 cycles to complete from cycle 4 through cycle 6. Thus, in cycle 5 and 6, the right stage must to be hold to do nothing because it has no data to work with. Meanwhile, the information in buffer 2 must remain inactive until the next stage has completed its operation. This means that stage 2 and in turn stage 1 are blocked from accepting new instructions because the information in B1 cannot be overwritten. Thus, step D4 and F5 must be postponed as shown. So the pipelined operation shown in this figure is said to have been stalled for 2 clock cycles, that is stalled. Here it is being stalled for 2 clock cycles. Normally, pipelined operation resumes in clock 7. Any condition that causes the pipeline to stall is called a hazard. We have just seen an example of data hazard. A data hazard is any condition in which either the source or the destination operands of an instruction are not available at the time accepted in the pipeline. As a result, some operation has to be delayed and the pipeline stalls. This pipeline may also be stalled because of the delay in the availability of instruction. For example, this may be result of a miss in the cache, requiring the instruction to be fetched from the main memory. Such hazards are often called as control hazards or instruction hazard. You can call it as control hazard or instruction hazard. The effect of cache miss on pipelined operation is shown in this figure. The instruction I1 is fetched from the cache in cycle 1 and its execution proceeds normally. However, the fetch operation from instruction I2, which is started in cycle 2, results in a cache miss. This instruction fetch unit must now suspend any further fetch request and wait for I2 to arrive. That is, it is being shown as ideal here. We assume that the instruction I2 is received and loaded into buffer B1 at the end of clock cycle 5. The pipeline resumes its normal operation at that point. An alternate representation of the operation of pipeline in the case of cache miss is shown in this figure. This figure gives the function performance by each pipeline stages in each clock cycle. Note that the decode unit is ideal in cycle 3 to cycle 5. The execution unit is ideal in clock 4 to clock 6 and the write cycle is ideal through clock 5 to clock 7. Such ideal periods are being called as stalls. They are also referred as bubbles in the pipeline. Once created as a result of the delay in one of the pipeline stage, a bubble moves downstream until it reaches its last unit. An example of structural hazard is shown in this figure. This figure shows how the load instruction, that is load x r1 comma r2 can be accomplished in 4-stage pipeline. The memory address x plus r1 is computed in step E2, that is here, in cycle 4, right? Then memory access takes place in cycle 5. The operand read from memory is written into register R2 in cycle 6. This means that the execution step of this instruction takes place 2 clock cycles, that is cycle 4 and cycle 5. It causes the pipeline to stall for 1 clock cycle. Here this particular place is nothing but of the stall, right? So it causes the pipeline to stall for 1 clock cycle, that is in clock cycle 4 and 5, because both the instruction I2 and I3 require access to the register file in cycle 6. See here, it is of completely ideal. Even though the instruction and their data are all available, the pipeline is stalled because one hardware resource, that is register file, cannot handle 2 operations at once. If the register file had 2 input ports, that is, if it is allowed 2 simultaneous write operation, the pipeline would not be stalled. In general, structural hazards are avoided by providing sufficient hardware resources on the processor chip. It is important to understand that the pipelining does not result in individual instruction because it is being executed faster. Rather, it is the throughput that increases, where the throughput is measured by the rate at which instruction execution is completed. At any time, one of the stage in the pipeline cannot complete its operation in 1 clock cycle. The pipeline stall and some degradation in performance occurs. Thus, the performance level of one instruction completion in each clock cycle is actually the upper limit for the throughput achievable in a pipeline processor organization. An important goal in design processes to identify all hazards that may cause the pipeline to stall and to find way to minimize their impact. So in this section, we discuss various hazards, starting with data hazard followed by control hazard. So in each case, we present some of the techniques used to mitigate their negative effects on performance. Let us first see about the data hazard. A data hazard is a situation in which the pipeline is stalled because the data to be operated on are delayed for some reason. We will now examine the issue of availability of data in some detail. Consider a program that contains 2 instructions, I1 followed by I2, right? When this program is executed in a pipeline, the execution of I2 can begin before the execution of I1 is completed. This means that the result generated by I1 may not be available for use by I2. We must ensure that the result obtained when the instructions are executed in a pipelined processor are identical to those obtained when the same instructions are executed sequentially. The potential for obtaining incorrect result when operations are performed concurrently can be demonstrated by some simple examples. Assume that A is equal to 5 and consider the following two operations. That is, what we have to do is, let us assume that A is equal to 5. Right? Now you consider the following two operations. When these operations are performed in the order given below, the result is B is equal to 32. That is A plus 3. We have assumed A is equal to 5. So A plus 3 is equal to 8. 8 into 4 will be equal to 32. Right? So will be equal to 32. But if they are performed concurrently, the value of A used in computing B would be the original value, 5 leading to an incorrect result. If these two operations are performed by instructions in a program, then the instruction must be executed one after the other, because the data used in the second instruction depend on the result of the first instruction. On the other hand, the two operations A into C and B is equal to 20 plus C can be performed concurrently because these operations are independent. Right? These two operations are independent. This example illustrates a basic constraint that must be enforced to guarantee correct result. When two operations depend on each other, they must be performed sequentially in the correct order. This rather obvious condition has far-reaching consequences. Understanding its implication is the key to understand the variety of design alternatives and trade-off encountered in pipelined computers. Consider this example. That is, here two instructions are being shown. That is, mul R2, R3, R4 and add R5, R4, R6. So this 2 gives rise to data dependency. The result of the multiplication instruction is placed into register 4, which in turn is one of the two source operand of addition instruction. Assuming that the multiplication operation takes one clock Assuming that the multiplication operation takes one clock cycle to complete execution, would proceed as shown in the figure. As the decode unit decodes the add instruction in cycle 3, it realized the R4 is used as source operation. That is, as the decode unit decodes the add instruction in cycle 3, right? As the decode unit decodes the add instruction in cycle 3, it realized that R4 is used as a source operand, because already we have taken an example in such a manner, that is, it has been stated as add add R5 comma R4 comma R6, and this R4 is being used to store the multiplication operation. That is what the example we have chosen, right? Hence, it is being realized that the R4 is used as a source operand while this is being decoded during the R3 cycle. Cycle 3. Hence, the decode step of the instruction cannot be completed while the right step of the multiplication instruction has been completed. Completion of step D2 must be delayed to clock cycle 5. It is delayed until the clock cycle 5 and is shown as D2A. It is being shown as D2A in the figure. The instruction I3 is fetched in cycle 3, but its decoding must be delayed because step D3 cannot be proceeded. Hence, pipeline execution is stalled for 2 cycles. So it is being stalled for 2 cycles here, right? So it is being stalled for 2 cycles. Next, let us see about operand forwarding. The data and hazard just described arises because one instruction, that is instruction I2 in the previous example, is waiting for a data to be written in the register file. However, these data are available at the output of the ALU once the execute stage completes the execution E1 step. Hence, the delay can be reduced or possibly eliminated if we arrange the results of instruction I1 to be forwarded directly to use in the step E2. The figure shows a part of the processor data path involving the ALU and the register files. This figure, right? This arrangement is similar to the 3-bus structure except that the register, source register 1 and source register 2 and the result register are being added. These register constitutes the interstage buffers needed for pipelining operations as shown in this figure, right? With reference to this figure, the register source register 1 and 2 are part of the buffer 2, right? This is nothing but it is a part of buffer 2 and the result register RSLT is part of buffer 3. The data forwarding mechanism is provided by the blue connection. The two multiplexers connected at the input to ALU allows the data and the destination bus to be selected instead of the connection of either SRC1 and or SRC2 register. When the instructions are executed in this data path, the operations performed in each clock cycle are as follows. After decoding instruction I2 and deducting the data dependency, a decision is made to use data forwarding. The operand now involved in the dependency register R2 is read and loaded in register SRC1 in clock cycle 3. In the next clock cycle, the product produced by instruction I1 is available in the register RSLT. And because of forwarding connection, it can be used to set E2, hence the execution of I2 proceed without interruption. Now let us discuss about the handling data hazards in software. We assume that the data dependency is discovered by the hardware while the instruction is being decoded. The control hardware delays reading register R4 until cycle 5, thus introducing a 2-cycle stall unless operand forward is used. This is being discussed in the example and it is also shown in the figure, previous figure. Right? An alternate approach is to leave the task of detecting the data dependency and leaving with them to the software. In this case, the compiler can introduce 2-cycle delay needed between the instruction I1 and I2 by inserting a simple no operation NOP. Right? So in this case, the compiler can introduce 2-cycle delay needed between the instruction I1 and I2 by inserting no op as follows, as it is being shown in this. If the responsibility for detecting such dependency is left entirely to the software, the compiler must insert the no op instruction to obtain a correct result. This possibility illustrates the close link between the compiler and hardware. A particular feature can be either implemented in hardware or left to the compiler. Leaving tasks such as inserting no op instruction to compiler lead to simpler hardware. Being aware of the need of a delay, the compiler can attempt to reorder instructions to perform useful tasks in the no op slot and thus achieves better performance. On the other hand, the insertion of no op instruction lead to large coding size. Also, it is often the case that a given processor architecture has several hardware implications offering different features. No op instruction inserted to satisfy the requirement of one implication may not be needed and hence would lead to reduced performance on different implementation. Next, let us discuss about side effects. The data dependency encountered in the preceding examples are explicit and easily detected because the register involved is named as the destination in instruction I1 and as source in I2. Sometimes an instruction changes the connection of register other than one named as destination. An instruction that uses an auto increment or auto decrement addressing mode is an example for it. In addition to storing new data in its destination location, the instruction changes the content of a source register used to access one of its operands. All the precautions needed to handle data dependency involving the destination location must also be applied to the registers affected by an auto increment or auto decrement operation. When a location other than one explicitly named in an instruction as destination operand is affected, the instruction is said to have a side effect. For example, stack instruction such as push and pop produces similar side effect because they implicitly use the auto increment and auto decrement mode. So the example is push and pop. So push and pop are the two instructions which can be taken as example for creating the side effect. Another possible side effect involves the conditional code flag which are used by the instructions such as conditional branches and add with carry. Suppose that the register R1 and R2 holds a double precision integer number that we wish to add to another double precision number in register R3 and R4. This may be accomplished as follows. Add R1, R3, add with carry R2, R4. An implicit dependency exists between these two instructions through the carry flag. This flag is set by the first instruction and is used in the second instruction which performs the operation. That is, we will be getting R4 is equal to R4 will be holding R2 plus R4 plus carry plus carry. Instructions that have side effects giving rise to multiple data dependency which lead to a substantial increase in the complexity of the hardware or software need to be resolved them. For this reason, instruction designed for execution on pipeline hardware should have few side effects. Ideally, only the content of the destination location, either a register or a memory location, should be affected by any given instruction. Side effects such as setting the conditional code flag or updating the content of an address pointer should be kept to a minimum. However, the auto increment and auto decrement addressing mode are potentially useful for the programmers. Conditional code flags are also needed for recording such information as the generation of a carry or the occurrence of overflow in an arithmetic operation. Next, we will see about unconditional branches. So this unconditional branches comes under instructional hazard. Now we are going to see about the instructional hazard. The purpose of the instruction fetch unit is to supply the execution unit with a steady stream of instruction. Whenever this stream is interrupted, the pipeline stalls as shown in the example what we have discussed previously. That is, there will be a catchy miss. A branch instruction may also cause the pipeline to stall. We will now examine the effect of branch instruction and the technique that can be used for mitigating their impact. We start with unconditional branch. The figure shows a sequence of instruction being executed in two pipelines. That is, the instruction I1 to I3. The instruction I1 to I3 are stored at successive memory addresses and I2 is a branch instruction. I2 is a branch instruction. Let the branch target be instruction IK. Let the branch instruction targets to IK. In the clock cycle 3, the fetch operation for instruction I3 is in progress at the same time that the branch instruction is being decoded and the target address is being computed. In clock cycle 4, the process must discard I3 which has been incorrectly fetched and the fetch instruction IK, and it fetches the instruction IK. In the meantime, the hardware unit responsible for the execution step must be told to do nothing during the clock period. Thus, the pipeline stalled for one clock cycle. The time slot as a result of the branch instruction is often referred as branch penalty. So, this is being called as branch penalty. Branch penalty. So the figure shows the branch penalty is one clock cycle. For a longer pipeline, the branch penalty may be higher. For this example, that is, in this example, the figure shows the effect of a branch instruction on 4-stage pipeline. Here it is of 4-stage pipeline. We have assumed that the branch address is computed in step E2. Branch instruction is executed at step E2. The instruction I3 and I4 must be discarded and the target instruction IK is fetched in clock cycle 5. Thus, the branch penalty is 2 clock cycles here. So, the branch penalty here is of 2 clock cycles. Reducing the branch penalty requires the branch address to be computed earlier in the pipeline. Typically, the instruction fetch unit has decided to have a dedicated hardware to identify a branch instruction and compute the branch target address as quickly as possible after an instruction is fetched. With this additional hardware, both of these tasks can be performed in step D2, leading to the sequence of events as shown in this figure B. In this case, the branch penalty is only 1 clock cycle. Here, the branch penalty is of only 1 clock cycle. Next is about instruction queue and prefetching. Either a catchy miss or a branch instruction stalls the pipeline for 1 or more clock cycles. To reduce the effect of this interruption, many processors employs sophisticated fetch unit that can fetch instruction before they needed and put them in a queue. Typically, the instruction queue can store several instructions. A separate unit, which we call the dispatch unit, takes instruction from the front of the queue and sends them to the execution unit. So the dispatch unit sends them to the execution unit. This leads to the organization as shown in the figure. The dispatch unit also performs the decoding function. To be effective, the fetch unit must have sufficient decoding and processing capability to recognize and execute branch instructions. It attempts to keep the instruction queue filled at all times to reduce the impact of occasional delays. When fetching instruction, when the pipeline stalls because of a data hazard, for example, the dispatch unit is not able to issue instruction from the instruction queue. However, the fetch unit continues to fetch instructions and add them to the queue. Conversely, if there is a delay in fetching instruction because of a branch or a catchy miss, the dispatch unit continues to issue instruction from the instruction queue. This figure illustrates how the queuing length changes and how it affects the relationship between the different pipeline stages. We have assumed that initially the queuing consists of one instruction. Every fetch operation adds one instruction to the queue and every dispatch operation reduces the queue length by 1. Hence, the queue length remains same for first 4 clock cycles. There is both F and D step in each of these clock cycles. Suppose that the instruction I1 introduce a 2 cycle stall as shown here, right? Since space is available in the queue, the fetch unit continues to fetch instruction and the queue length rises to 3 in clock cycle 6. The instruction I5 is a branch instruction. It targets instruction IK. Is fetched in clock cycle 7, and the instruction I6 is discarded. This is being completely discarded. The branch instruction would normally uses a stall in cycle 7 as a result of discarding instruction I6. Instead, the instruction I4 is dispatched from the queue to the decoding stage. After discarding I6, the queue length drops to 1 in clock cycle 8. The queue length will be at this time until another stall is encountered. Now observe the sequence of the instruction completion in this figure. Let us now observe the sequence of instruction completion in this figure. The instruction I1, I2, I3 and IK completes execution in successive clock cycle. If you see it, the instruction I1, I2, I3 and this IK completes the execution in the successive clock cycles. If you see it, you can see that. This I4 also. So the instruction I1, I2, I3 and IK are being completing their execution in the successive clock cycles. Hence, the branch instruction does not increases the overall execution time. This is because the instruction fetch unit has executed the branch instruction concurrently with the execution of other instruction. This technique is referred to as branch holding. This kind of technique is being called as branch holding. Let us now discuss with the conditional branch and branch prediction hazards. A conditional branch instruction introduces the added hazard caused by the dependency of branch condition on the result of preceding instructions. The decision to branch cannot be made until the execution of the instruction has been completed. The location following a branch instruction is called branch delay slot. There may be more than one branch delay slots depending on the time it takes to execute a branch instruction. The figure shows two branch delay slots here. That is, for example, there are two branch delay slots in this figure and one branch delay slot in this figure. The instruction in the delay slot are always fetched and at least partially executed before the branch decision is made and the branch target address is computed. A technique called delayed branching can minimize the penalty incurred as a result of conditional branch instruction. The idea is simple. The instruction in the delay slot are always fetched. Therefore, we would like to arrange for them to be fully executed whether or not the branch is taken. Now, consider the instruction sequence given in this figure A. The register R2 is used as a counter to determine the number of times the content of register R1 is shifted left. For a process with one delay slot, the increment can be reordered as shown in this figure B. The shift increment is fetched while the branch instruction is being executed. After evaluating the branch condition, the process fetches the instruction at loop or next, depending on whether the branch condition is true or false, respectively. In either case, it completes execution of the shift instruction. The sequence of events during the last two phases in the loop is illustrated in this figure. That is, pipeline operation is not interrupted at any time and there are no ideal cycles. Logically, the program is executed and if the branch instruction were placed after the shift instruction, it is also being executed. That is, the branch takes place one increment later than where the branch instruction appear in the instruction sequence in memory. Hence, the name delayed branch. Another technique for reducing the branch penalty associated with the conditional branch is to attempt to predict whether or not a particular branch will be taken. The simplest form of branch prediction is to assume that the branch will not take place and to continues to fetch instruction in a sequential address order until the branch condition is evaluated. Instruction execution along the prediction path must be done on speculative basis. Speculative execution means the instructions are executed before the process is certain that they are in a correct execution sequence. Hence, care must be taken that no processor register or memory location are updated until it is confirmed that these instructions should indeed be executed. If the branch decision indicates otherwise, the instruction and all their associated data in the execution unit must be purged and the correct instruction fetched and executed. An incorrect prediction branch is shown in the figure for 4-stage pipeline. The figure shows a comparative instruction followed by branch instruction. The branch prediction takes place in cycle 3 while the instruction I3 is being fetched. The fetch unit predicts that the branch will not be taken and it continues to fetch instruction I4 as I3 enters the decoding stage. The result of the compare operation are available at the end of the branch at the end of the cycle 3. Assuming that they are forwarded immediately to the instruction fetch unit, the branch condition is evaluated in cycle 4. At this point, the instruction fetch unit realized that the prediction was incorrect and the two instructions in the execution pipe are purged. A new instruction IK is fetched from the branch target address in clock cycle 5. If branch outcomes were random, then half the branch would be taken. Then the simple approach of assuming that branch will not be taken would save the time lost to conditional branch of 50% of the time. Now let us discuss about the dynamic branch prediction. The objective of branch prediction algorithm is to reduce the probability of making a wrong decision to avoid fetching instruction that eventually have to be discarded. In dynamic branch prediction schemes, the processor hardware assesses the likelihood of giving branch being taken by keeping track of branch decision every time that instruction is executed. In its simplest form, the execution history used in predicting the outcome of the given branch instruction is the result of most recent execution of the instruction. The processor assumes that the next time the instruction is executed, the result is likely to be the same. Hence, the algorithm may be described by two state mechanisms as branches likely to be taken, that is LT. LT is nothing but of branches likely to be taken, and LNT is nothing but of branches likely not to be taken. So this is branch is likely to be taken and this is branch is likely not to be taken. Suppose that the algorithm is started in the state of branch is not likely to be taken when the branch instruction is executed and if the branch is taken. The machine moves to the state of LT, that is likely to be taken. Otherwise, it remains in the state of LNT. The next time the same instruction is encountered, the branch is predicted as taken if the corresponding state machine is in state LT. Otherwise, it is predicted as not taken. This simple scheme, which requires one bit of history information for each branch instruction, works well inside program loop. Once a loop is entered, the branch instruction that controls looping will always yield the same result until the last pass through the loop is reached. The last pass, the branch prediction will turn out to be incorrect and the branch history state machine will be changed to opposite state. Unfortunately, this means that the next time this same loop is entered and assuming that there will be more than one pass through the loop, the machine will lead to the wrong prediction. Better performance can be achieved by keeping more information about execution history. An algorithm that uses 4 states thus requires 2 bits of history information for each branch instruction is being shown in this figure. The 4 states are ST is nothing but of strong likely to be taken, LT is nothing but of likely to be taken, and LNT is nothing but of likely not to be taken, and SNT is of strongly likely not to be taken. Again, assume that the state of the algorithm is initially set to LNT. After the branch instruction has been executed and if the branch is actually taken, the state is changed to ST. Otherwise, it is changed to SNT. As program execution progresses and the same instruction is encountered again, the state of branch prediction algorithm continues to change as shown. When a branch instruction is encountered, the instruction fetch unit predicts that the branch will be taken if the state is either LT or ST, and it begins to fetch instruction at the branch target address. Otherwise, it continues to fetch instruction in a sequential address order. So that's all with pipelining and pipelining hazard. Meet you all in the next video lecture. Thank you.